So it's great to have Anna give us her last lecture on the introduction to lattice field theory. You know, 1 hour and 15 minutes, and we'll ask questions as we go along. Go ahead.
Absolutely, please. Good. I would like to spend the last lecture discussing applications of what we have discussed so far. In particular, how do we connect the renormalization group that we understand and know well in the continuum versus renormalization group on the lattice that is more Wilson RG based and offers the possibility to calculate non-perturbative quantities. So this is, oops, here we go. This is the picture it kind of ended last time, that is comparing the, oops, all right, my pen is not working, I apologize for that. Let's see if it is better now. Comparing the perturbative beta functions in confining and conformal systems to the analog that we expect on the lattice. Now, the reason we don't draw a simple one-dimensional beta function is that on the lattice we understand or we try to include the emerging or possible relevant operators. So I think we discussed this picture actually last time, where the continuum system is conformal. It has 3 fixed points: the Gaussian, the infrared, and the ultra, and then emerging new ultraviolet fixed point. And in an extended parameter space where the relevant operator emerging from the new fixed point is denoted by capital G here. We still have the 3 fixed points. There is the phase separation between the weak coupling and strong coupling phases, and we have discussed how to go from the perturbatively assumed or hypothesized picture to a lattice description. Now, the middle picture here is kind of is part of what conformal system is. It is the opening of the conformal window. We want to describe what happens to the fixed points as the conformal window opens. If you look at the picture on the left, really what happens is that the infrared and UV fixed points move in, and when they merge, when they collide and merge, that's when conformality gets lost. So this is the instant that is described by the middle diagram here. And let's look at what is the analog of that on the lattice. The merging of the infrared and a new ultraviolet fixed point is described by here, where the infrared fixed point simply enters into the UV fixed point. It has to be on a critical surface, so the UV fixed point cannot move away from the critical surface. The only thing that can happen is the infrared fixed point merges with the UV fixed point. It's a very interesting picture, but not unheard of. Condensed matter people looked at merging fixed points for a long time. It is well understood it can happen. We just have not seen it yet in 4-dimensional systems. Then it's interesting to ask, yes.
I can ask you a question. When you do it in 1 dimension, it's clear that the merging and splitting of fixed points is controlled by Morse theory, because in 1 dimension, that's what it is. If you have a minimum, you get a maximum afterwards. But is there a similar notion on the higher dimensional that when fixed points merge, they kind of disappear or anything like that?
I think it's all just hypothesized. There is one example that I am aware that is worked out in detail for the two-dimensional Potts model. That's a paper by, or work by, Gorbenko and Slava, where they showed that when the fixed points there merge, they split up into the complex plane and leads to a first-order phase transition and at the same time to some kind of walking behavior because they are still present, but in the complex plane, so they influence the flow. But that's the only example I know that is explicitly worked out.
Thank you.
I thought the complex plane was when you were near conformal, but after you hit the conformal point, do they say anything about it splitting up into two fixed points the way you have it?
So I
mean, their calculation is near conformal. Before you get there, they're two complex plane things that then merge into the fixed point. But I don't know, do they say something about the post?
I have to review it. I haven't thought about this paper, but indeed, when we have walking, that is the beta function is just a little bit below. That's when we have complex fixed point.
Yeah, that's the middle diagram, but the one on the right is even harder to. I mean, I don't know what
this one. So at this point, I really don't remember what Richkov and Gorbenko are doing. I think they considered the merge, but you might be right that they didn't. I know that Igor Herbut, who is a condensed matter theorist, has looked at merging fixed points, perturbatively mostly, in different models. But no, it's a great question. I think that there isn't a lot of explicit calculation for that, and we really don't quite know what happens or how it happens. So I am now on uncharted territories because even the idea that the conformal window opens up with this quadratic beta function is just a hypothesis. The question is that what can we do on the lattice to prove or disprove, identify or show it, and otherwise if a picture like that could happen. Does it make sense?
Yes.
Okay. Interrupt me because, again, as I said, what I said in the very first lecture, that is solid. The second lecture, that was just Wilsonian RG. Today, I will show things that are more in that's the direction we could be moving and learning new physics or new phenomena kind of thing. So it's less solid and less well established. But let me move to the first diagram, which is that just QCD-like chirally broken confining system. So the question is that what happens on the lattice as we move from the merged fixed point to a system where we don't have a fixed point, we don't have where we have chiral symmetry breaking. Again, it's a hypothesis that most likely what happens, again, as consistent with this picture here, that the fixed points or the lines, the renormalized trajectory and this transition line will split. They will just go by each other, avoiding contact and avoiding a fixed point. But we really don't know if any of these really happens on the lattice. So how can we test? The idea is that continuum physics is what we have on the renormalized trajectory. So we want to measure or we want to calculate what numerically, if we can see what happens on the renormalized trajectory and perhaps even identify the fixed point and the phase that is on the strong coupling side of the fixed point. If we can do that, then we should be able to actually recover the one-dimensional beta functions that we understand a little bit better. All we need for that is an RG block transformation that we can do and measure the trajectory or the properties of the RG flow. So that is where we connect to what we did last time. Critical phenomena and Wilsonian RG. We want to do a Wilsonian RG and calculate the RG behavior of the system. So again, just a reminder, we start with original fields, we block them. With that, we decrease the degrees of freedom, and then we rescale to have the original size. A well-defined procedure. The last rescaling step simply sets X, every dimensionful quantity divided by B or rescaled by B. In a particular, the lattice volume will be rescaled by B as well. Now that's a bad sign, because typically we can't start with very large volumes. We start rescaling it by factors of 2. Pretty soon we run out of lattice. In addition, if B is 2, it will be really difficult to calculate a continuous derivative. That's why Wilsonian RG, or what we did back in the 80s, 90s, the Monte Carlo renormalization group, didn't really take off, because it was numerically too difficult to do discrete blocking steps. Now that has changed with the introduction of gradient flow. Gradient flow was introduced by Lucher back in 2010 for very different purpose. He basically tried to do an improved lattice action or simulation method, and then eventually explained how gradient flow can be used to do scale setting in lattice calculations. But gradient flow actually can be recast as a continuous renormalization group block transformation. So what is gradient flow? For a scalar model, it is simply a kind of a diffusion equation. The flow time is denoted by T, and I'm sorry for that, but from now on, T is not going to be time, it is going to be gradient flow time. So the flow equation is a diffusion equation in the gradient flow time. And on the other side, the space part of the diffusion is driven by the derivative of the action, but it could be something much simpler, just a quadratic form. Just think about it as a diffusion equation. We start with our original field configuration and then solve this diffusion equation. If we have a free flow, that's very easy to explicitly solve the equation. And in fact, in momentum space, we simply pick up an exponential suppression of the field, and in real space, in position space, we get, you might recognize it is the kind of smearing that I had last time, that is take fields at distance s from where we start from, give them a weight factor e to the minus s squared t. So we have an exponentially decaying function f that we weight the neighboring fields and integrate it over. That's exactly what we envisioned, or Ken Wilson envisioned, as a block transformation. So this is great. This is what we were looking for. The beauty here is now that we have this variable t, flow time t, that is continuous. So we can do the block transformation or the RG transformation continuously. For completeness, I did write down how the gradient flow looks for gauge fields, pretty much the same diffusion equation. Fermions are similar, they sit on top of the gauge field. One quantity I would like to introduce is the so-called renormalized gauge coupling. It's really nothing else but the energy density, the flowed energy density multiplied by the flow time square times the normalization constant. Now, why is that called a renormalized gauge coupling? If you do a perturbative calculation and set this normalization constant correctly, then this quantity will be identical to the MS bar renormalized coupling at tree level. And then one can do higher order calculations and show that this is simply a new definition of the renormalized coupling. We can think about it as a new scale or renormalization scheme. I should also mention at this point that this energy density, which is really just F unit squared, can be expressed in terms of closed Wilson loops like the plaquette. Or we can use other Wilson loops. It really doesn't matter. Within up to cutoff effect, this is a perfectly good definition for this quantity. Good. So now we have a definition of a flow, gradient flow, that looks like that it will make for us block spins or blocked quantities. Is that enough? Well, not quite, because for a proper RG transformation, we need a rescaling. That's the step that is this last step here in this slide, and that is not part of the gradient flow. So gradient flow, strictly speaking, is not an RG transformation, but it can be mimicked when we take expectation values numerically, and then it becomes a perfectly well-defined, correct RG transformation that is continuous. Now, if you have a continuous RG transformation, then we can use it, going back to here, we can use it to measure or follow the flow along the renormalized trajectory. All we need for that is an operator that really measures how far the flow has progressed along the trajectory. And a little bit of thinking shows that, in fact, any coupling will work for that is dimensionless. We cannot afford to have a dimensionful coupling because that picks up extra factors as we do an RG transformation. But if we have a dimensionless coupling, no canonical and no anomalous dimension, that coupling will really track how we move around the RG trajectory. And that's exactly what this gradient flow coupling is. It's important, or well, for me, it was useful to realize that once we have an operator that is expressed from SU3 projected plaquette expectation value, that operator cannot have an anomalous dimension because it's simply always projected back to SU3. So that is a reason why it is a well-defined gauge coupling, and we can use it to track the progress along the renormalized trajectory. And then, of course, we can just take its derivative with respect to the flow time. This minus sign is here because t is actually has dimension of -2. That is, it's a length square dimension. So if I want to define the beta function the usual way, I have to put in a minus sign. The 2 is okay. That would be the analog of mu squared, the dg squared over d mu squared. So the factors of 2 are correct, but we need a minus sign. Good. So now we have a block transformation. We have a well-defined quantity we want to calculate with a well-defined operator. You can just go there and do it. Of course, the Devil is always in the details, and in the lattice calculation, those can be serious. One has to do infinite volume, zero mass, because we cannot afford another relevant operator in the system. And one more thing, we need to have large flow time, otherwise we won't reach the renormalized trajectory. We have to wait until the irrelevant operators die out in order for this system to work. But we know what we need to do, and I really, in the next few slides, I want to show you a couple of examples of how it works. Any questions before I get into numerical results? We are all happy. Good. So here is the first one. That's the beta function, and I call it continuous beta function, but it is really what we are used to in the continuum. Just the beta function, and this is for pure Yang-Mills, no fermions. And the beta function as the function of alpha g squared over 4 pi. So if you look at the numbers here, this system really goes out to very strong couplings. Alpha 2 is g squared about 24. Now, MF0, pure Yang-Mills, is a confining system. We know approximately where confinement sets in, somewhere around here, less than alpha 1. So this area is really showing how the beta function looks in the deconfined regime, but this area is fully confined. Now, what do you see here? The colored data points are various raw data, continuum limit extrapolated data. The important thing to notice is this line here, which is basically the, oops, that's not what I wanted to draw here, which is the continuum prediction for the beta function. The various black lines represent the one-loop perturbative, two-loop perturbative, three-loop MS bar, three-loop gradient for perturbative results. What you can see from this plot that that the numerical data is not following any of the higher loop perturbative prediction. This one is the three-loop MS bar that's really far away from the numerical data. We are okay in the weak coupling regime. Then it really follows the perturbative predictions, but it is totally off in the strong coupling confining regime. Nobody expected that. The expectation was that the perturbative results will be more, or perturbative predictions will be more robust, but it's not. There is another observation here that I want to make. Look at this line. It's about S linear gap. That is the beta function seems to be proportional to g squared, maybe with a constant. Again, that is very non-perturbative. In the weak coupling, the beta function starts with g to the 4, and then there are higher order terms, higher order polynomials. So what makes the beta function linear in g squared, or almost linear in g squared? And at that point, I have to say that I will do even more speculation than before. So why is it that the beta function is more or less linear? First of all, what does it mean? If the beta function is linear in g squared, we can integrate it out. If I invert it, dg squared over alpha g squared plus c integral is proportional to dt over t. And if I solve this equation, I find a relation that simply states that g squared is proportional to T, the flow time, or the energy scale to the power of alpha plus a constant. If you look at this plot here, so you don't see it, but I will tell you that alpha, this constant here, is close to 1, not quite 1, it's around 1.2. So can we understand why? Is there any physical meaning why the beta function is linear, or why G squared scales as T almost as a homogeneous function of T? When we first showed or published this beta function, I got an email from Gary Schierholz, who claimed that this is all topology. Maybe, but let me show what could it be, what it could be. So if you have a beta function that is alpha G, that suggests or that implies that G squared should behave as T to the alpha plus constant. We measure G squared. So how does it look? I decided not to put in a plot, but anyone who has done lattice simulations have seen that if we look at G squared as the function of the flow time, and the flow time is not enormously large, then typically it is a section which is really just UV cutoff effect, and then an almost linear behavior. So indeed, numerical results suggest that alpha is very close to 1, and G squared is indeed linear in alpha. So it's not very surprising. There is one other thing that we can look at. We can look at different topological sectors. And that's not usually done, but just because, I don't know, people didn't think about it or didn't need it. So look at different Q topological sectors. What one sees is that the beta function, or this G squared, actually will break up into different sectors depending on the topological charge. So indeed, there could be something to the topology. Can we understand that? How could it work? So what do we know about the instantons of the vacuum? Well, we know that if we have an instanton, just a well-separated instanton bump, it will contribute to a well-defined energy, to the energy of the system. That is, if I take the energy density, I can write it as the energy density without any topology, plus the number of topological objects times this energy of a single instanton divided by volume, because we're talking about energy density. That's a fairly straightforward, you can't go wrong argument. So again, empty now is the total number of instantons, both instantons and anti-instantons. Now the gradient flow coupling is T squared E. So let's multiply this expression here by T. What do I get? The gradient flow coupling without topology plus a term that is T squared times the number of topological objects divided by the volume. Now it comes interesting here, because if this ratio MT over V remains finite in the infinite volume limit, then the topology contributes, most likely dominates the gradient flow coupling at large time. So it is quite reasonable to assume or think that what we observe in the beta function could be indeed topology related. So let's see how it works. Really the question is, what happens to the total number of topological objects, not the net charge, not instanton minus anti-instanton, but the number of objects as we increase the volume and change the flow time. Now, what are the possibilities? In the QCD vacuum, we could have separate instantons or anti-instantons, or we could have pairs, relatively close pairs, or more likely, and that's the physical picture, we have instantons, anti-instantons that are closely interacting. They have an overlapping wave function. That is what's necessary for chiral symmetry breaking. That's what we learned, well, basically random matrix theory, instanton gas model, whatever. Good. So these are just three different possibilities for the instanton vacuum. What happens as we do gradient flow? Gradient flow is a smoothing transformation. It averages the nearby spins or fields together. If we average these two guys together, let's go back, so a plus, minus, minus, plus. If I average those two guys together, they will go to nothing. They annihilate. And we see that very clearly on, actually, that's what I wanted to say, these annihilate. If we have a, if here I wanted to really, show, separate, where separated instantons, these guys don't do anything. Gradient flow will most likely preserve that. But again, that's not what we expect in the QCD vacuum, because we need the overlap. Now, if I take at the overlap form, what happens there? Some of those guys will annihilate. They are nearby. But not all. I really just need an overall overlap between in between the entire regime. So this thing could still end up in a system that has several positive and negative charges. That is, we have a total number of instantons that is not identical to the topological charge, which is just the instanton minus anti-instanton number. So these are the possibilities. Let's see how it looks. If it turned out that the total number of topological objects actually reduced to the number of unpaired instantons, that is topological charge, if NT was proportional or was equal to Q, we know that Q scales as the square root of the volume. So as we take the infinite volume limit, NT over V would scale as 1 over the square root of the volume. It goes to 0. It does not contribute. On the other hand, if that's not what we observe in numerical simulation, so we have to accept that NT is not going to be just Q. Now, what can we say about the Q0 sector, that is, or the NT0 sector, the sector where we don't have any topological object? That is just like a conformal system, and there we know that T square E goes to a constant. That's what we expect, that the fixed point value, that's what we see on the lattice. So these are the vacuum fluctuations at the cutoff level. If this property survives going into the confining regime here, then what we expect is that if T square is proportional to T, that's the numerical result, then NT over V will have to go as 1 over T to satisfy the observed behavior of the energy density. That is, what we see here is that the number of topological objects will decrease as we increase the number of gradient flow steps, but it will increase in a very specific form, it will increase as 1 over the flow time. And that can be consistent only with this kind of setup, where we have some pairs that annihilate, but some of them remain well separated, and only at very large flow time will they move together and get annihilated. So that's a very interesting possibility. It should be or can be studied on the lattice. I haven't, the only paper I've seen and that really didn't address many of these questions is this Nakamura-Schierholz paper, but I am just throwing it up as something that could be very interesting to give information about the QCD vacuum. Again, I have to say these are all speculations. But I am very excited to learn if any of that is correct. Good. Now, so again, where this entire discussion come from the observation that the beta function had a very unexpected, non-perturbative linear behavior that suggested a constant plus an homogeneous term in the flow time. And that was with 0 flavor. I have results, in fact, I have fairly new results with 2 flavors. So now we have fermions. You might not see it very clearly, but we have a beta function here, this red line, that surprisingly, again, is, here we go, looks linear. I just put it at this point a linear line, just a straight line that covers most of the beta function at strong coupling. Again, the weak coupling regime, which is deconfined, is somewhere here, and then the confining regime is here. We are going up to fairly strong coupling. So again, the beta function seems to be linear. There is one interesting difference, that now the slope is almost exactly 1. It was 1.2 before, it changes now to 1. If this linear slope is indeed instanton driven, this is the effect of the fermions. The fermions, we know, pull the instantons together, introduce an interaction that eventually leads to chiral symmetry breaking. That's all I know about it. It is a relatively new result, even the beta function, but I hope maybe next time we'll have more to say about it. I want to show another plot. It is pretty much the same as the one before, but I am showing the beta function divided by g to the 4. Now, because the beta function starts as d0 g to the 4 plus higher order terms, now the 1 loop prediction is just this constant here. The 2 loop is the one going down. This is the 3 loop gradient flow. So that dividing it by g to the 4 really brings out what happens at small g square. And interestingly, it is the small g square region that is the hardest to calculate here. So that is where we have the hardest time to get a good prediction. The strong coupling regime, which is really this part. First of all, the beta function is not small and the errors are very small. Now, why am I showing this? Because at this point, we actually could calculate the QCD lambda parameter at the energy scale of determined by T0, which is a quantity where G square at T0 is this normalization constant times 0.3. That's the quantity we use on the lattice to set the scale. We have actually done that. I didn't write down the number in here, but it's a beautiful curve. What do we do? So the lambda parameter is basically e to the integral of the 1 over beta function dg squared plus or some constant terms. It can be done. We actually determine lambda QCD in the gradient flow scheme, compared it to the MS bar scheme, and the values agree pretty closely to what other methods predicted. So this is a viable alternative, possibly a better alternative than other things to get the lambda parameter.
Anna,
Good.
I have a conceptual question.
Mm-hmm.
Usually, the parameter T is roughly something that goes to the infrared, right? When T gets
Mm-hmm.
bigger. Usually,
Yes.
when we have something like a mass scale where some mass gets generated, usually we change to some effective field theory on the bottom and we do some matching. And usually the beta functions stop making sense once that mass scale is generated. This seems different, so I'm trying to understand the difference.
So good. It's why can we get away with just calculating the beta function? So why don't we have to stop
right
in here? Yes. So one thing is that actually we have to do. Let me think of how to answer that. So one thing that we have to do, we really have to go to the infinite volume limit. So even if we have another mass scale, which could be lambda QCD, which could be psi bar psi or something like that, it is only just one length scale, so we can take T and psi bar psi and work with that together. In the decoupling regime, we frequently connect T and L, that's the step scaling function, and we can do that as long as those are the only two relevant length scales. So I think what I am trying to say is that if I take the volume to infinity, then I am not restricted if other length scales show up, but I have to think about it. That's a good question of how to answer it. So in some sense, if I go back, and I don't have it here, the beta function, no, I don't have it. So if I think about of what we are doing, let's try to draw it in here. So in the RG picture, I have a fixed point, a renormalized trajectory. I start from my direction, follow the trajectory. That is not sensitive of what the system is, whether it is chirally broken or not. So I can run this trajectory, especially if I am in infinite volume. I am always in the chirally broken regime, yet I can still draw the RG picture.
I'll have to think about it, but thank you.
I think about it too. I understand what you are asking, and I think it's a very relevant question, but this is my best explanation. And I think it's important that what we are doing here is really in the infinite volume regime. The only thing is that whether the coupling is small, that is below the confinement scale or above the confinement scale, but the RG trajectory of RG flow itself is not. I don't think it cares about that. So let's. I am happy to think about more and discuss it more.
Thank you.
Good. Now, anything else? Because I want to change gears a little bit. I want to talk about anomalous dimensions of operators. So up till now, it was the beta function. And obviously, one can try to do that So I showed you 0 and 2, we have a higher number of flavors. But instead of going there, I want to talk about composite operator anomalous dimension. Okay. What is the idea here? That if I can, the goal is to calculate an anomalous dimension as the function of the running coupling. Now, we can't do that on the lattice. What we can do on the lattice, we can calculate the running coupling as the function of this flow time or energy scale. If we can similarly calculate an anomalous dimension, and here I mean anomalous dimension for psi bar psi or similar operators, mesons or protons or baryons, if I can calculate the anomalous dimension for a composite operator again as the function of the flow time, then I can combine these two and basically eliminate the flow time and calculate gamma as the function of G square. And that is what we can compare to perturbation theory, because that's what is typically determined perturbatively. So the idea is, how can we do that on the lattice? What is the method to calculate gamma as the function of the flow time? Because we have already done G square as the function of the flow time. How do we get an anomalous dimension for an operator? If I have an operator O and I take a 2-point function, a correlator, and it's a funny notation, but all it means is that I am taking 0 spatial momentum correlators. One of them is not flowed, that is t is 0. The other operator is flowed, that is at t equals t. One operator is sitting at the fourth dimension 0, the other is sitting at fourth dimension x4. That's how I measure the correlator. That is my G x4 t. Now, if I do an RG transformation with scale change b, which is proportional to the square root of flow time t, the R equation is well known. It's simply the couplings change from original coupling to float coupling. X4 decreases by a factor of b, that's the rescaling, and we pick up a scale factor b to the minus delta, where delta is the dimension, the scaling dimension of the operator O. It could be simply the canonical engineering dimension plus the anomalous dimension, or it might be an extra factor eta added to it if the transformation, RG transformation is linear. That is basically the wave function renormalization factor or anomalous dimension of the fermions. The problem is this is eta, which we don't know a priori. But if we choose an operator that has no anomalous dimension, like the vector, then taking the ratio of our desired operator G of O with the vector operator V will lead to a relation where, in fact, not only eta, but the delta or the D cancel as well. So that will be just a D to the power of minus G, the gamma O, the anomalous dimension of O. And from this relation, it is straightforward to determine gamma. So the only trick we have to do here is to normalize everything with an operator that has no anomalous dimension and will cancel the unknown eta exponent. So I wrote it down one more time. If I now take the logarithmic derivative of this ratio, that will predict gamma O at flow time t, and that was our goal at the get-go. if I want to turn it into a wave function, into a matching factor, Z factor calculation, we have to do something very similar. That's what we do for the lambda parameter, that is integrate 1 over the beta function times gamma, do a matching perturbatively. This is something we are working on, and hopefully we'll have a publication in a couple of, I would say, weeks. So expected by the end of the year. Good. So how does it look? I want to show some results. This is 2 flavors, and the first plot is the mass anomalous dimension as obtained from the pseudoscalar. So these are domain Wolf fermion calculations that preserve chiral symmetry. So we know that the pseudoscalar has the same anomalous dimension as the mass, as the scalar as the mass. What you see here is gamma as the function of G square, as I said, and there are a lot of different colors in there. Those are raw data, but the predicted continuum limit is this pink line underlying it. It's a very well-defined continuum limit. Interestingly, what are the different black lines? This one, actually, I might have messed this up. Okay, this one is one loop perturbative prediction. This one is 2 loop perturbative prediction for gradient flow. And again, the predicted gamma tends to follow the 1 loop prediction closer. We don't understand why. We don't understand why it is not going to 2 loop or even higher loop, but that's what it does. And then on the next plot, I have the same thing for the proton. Now that's interesting. In QCD-like systems, it would be related to the proton decay. In DSM systems, not with 2 flavors, but with the in conformal systems, that anomalous dimension is essential if we want to do all right, okay, what do I want to do? Partial compositeness calculation where the proton anomalous dimension has to be large, where the 3-point function has, or the 3-point operator has to become relevant. Now again, what you might see, it's a mess because we have not cleaned it up yet, but the predicted anomalous dimension in the continuum limit is this pink line underneath. It again is very close to the 1 loop perturbative prediction. There is absolutely no sign of any kind of non-perturbative enhancement. And observe that this is C²15. This is really deep in the non-perturbative regime. That's just how QCD wants to behave. Now maybe conformal systems will be different. And I have a plot for a conformal system, 10 flavors. My student Curtis Peterson showed this plot in his Lattice talk a couple of weeks ago. So what we have here is the pseudoscalar, the tensor, and the proton, all 3 operators together on the same plot. That is the pseudoscalar, that's the tensor, that's the proton. And again, what we see that all 3 operators have an anomalous dimension that is very close to the 1 loop universal prediction. Again, we don't go out that high in G square, but G²8 is a reasonably strong coupling. We see no enhancement of the proton anomalous dimension. So this model would not be a good candidate for partial compositeness. Now you might say that if this is a conformal system, how do we see that it's conformal in this plot? We don't. In fact, if you think about it, if I take the anomalous dimension gamma as the function of G squared, that will just keep on going. The flows, of course, if I would do flows in the flow time, they would turn around, but the value of gamma is totally insensitive to that. It goes through the possible infrared fixed point just the same. I would need to look at the beta function, which is this plot down here. And when the beta function develops an infrared zero, that's where the gamma universal anomalous dimension can be read off. But for that, we really need the beta function from the gamma itself. That cannot be done. So that's an important observation to keep in mind. Now, what do I think based on calculations of other quantities of where the infrared fixed point is in this system? It is somewhere between 10 and 12. We don't have a very good prediction. So it is somewhere between 10 and 12. The anomalous dimension does not go out that far, but it would be hard to imagine that this curve, just continue pretty much straight, because that's what it has been doing. So it seems that the anomalous dimensions are just totally insensitive to non-perturbative effects, which is quite different from the beta function that showed a very different behavior. Good. So I have some more material, but you see, I just said it if I have time. So let's stop here and see if there are other questions or comments about the beta function, gamma function, how we do gradient flow.
Any questions? There's no questions in the audience right now, so.
Okay, all right. If there is no question, let me spend. Okay. We have discussed a lot of things, and I think that what is what we learned from using this gradient flow continuous renormalization group transformation is what in the future might give us quite important information both for composite and QCD-like systems. What I would like to do in the next 10 minutes or so is go back to what I could not finish in the first lecture, and something that I would like to use on Tuesday when I have a 30-minute more science talk, and that is strong coupling expansion. Now, strong coupling expansion is something we did when we didn't have computers back in the good old days of when Lattice really started. But I truly believe that strong coupling expansion can give physical insight of what we expect, and even might give suggestions of how to improve things non-perturbatively and numerically. So what is a strong coupling expansion? What can be expanded? So this is, I wrote down again the two actions that I discussed. The top one is the staggered fermion action. The bottom one is the Wilson fermion action, and in both cases I have just the simplest gauge interaction. I can do strong coupling then. I can have beta small, and remember beta is 6/G0 square here, the bare coupling. So beta small is G, the bare coupling large. I can do an expansion When we do that, we basically, if beta is 0, then this term is not there at all. Then all I have, the gauge field shows up in the linearly in the interaction of the fermions. I can integrate it out. That's a trivial integration. What we get is a fermion action that contains 4 fermion fields. Now, these 4 fermion fields are exactly what we are looking for when we look for example, new interactions that might trigger new symmetry breaking or new kind of phases. So this is interesting to look at. It's a non-trivial 4 Fermi interaction, but it certainly leads to the kind of actions we are looking for. If anyone listened to Simon Catterall's lecture from last year, or whatever he is doing this year, he's always looking for 4 fermion interactions to lead to symmetric mass generation. And I think this is how it might emerge in a lattice calculation. Now, the other limit we can take is when we keep beta, that's fine, but we integrate out the fermions. The fermions are quadratic, and the fermionic integrals are usually easy anyhow. What we can do is do an expansion either when m is large, or alternatively this kappa here, and remember kappa was 1 over 8 plus 2m, when kappa is small. So this is an expansion in terms of 1 over the fermion mass, or in terms of kappa, and because of that, because kappa describes hopping of the fermions, it's called hopping parameter expansion. I want to show it a little bit more explicitly because I'd like to use it, use this on Tuesday. So let's take the Wilson fermion action. Here is kappa. If I take the action or the functional integral and simply expand the hopping, exponential hopping term, the sum over n location and direction will turn into a product. And then I have 1 minus kappa times the hopping term plus kappa square plus higher order terms. At some point, this series will terminate because these are fermions. I can't put more than 1 at a side. And then I just have the Gaussian term e to the psi bar side, still in the exponential. So at this point, I can integrate this out. The only way to get a non-zero result, if I have a psi and a psi bar and a psi at one location, let me say it differently. If I have a term from this hopping parameter expansion that has a psi bar u psi hopping around, I have to put another psi bar here, otherwise the fermion integral will be 0, and of course it will have a u term to it and another psi, and the only way to close this is to form a closed loop going around with the hopping term psi and psi bar. So these are, when we integrate as the fermions, what I will get is sum over closed loops, closed gauge loops. The lowest, and in fact that's what I am trying to write down here, when we re-exponentiate it, we actually get an effective gauge action. It's a relatively straightforward exercise to show that the leading term of this re-exponentiation is just another plaquette term, the same as the gauge action we started with. But then, of course, there will be terms with 6-link and the terms with whatever more complicated loops there are. But they are all suppressed with powers of kappa. So this is an expansion in kappa. If kappa is small, it's a fairly convergent expression. This is the hopping parameter expansion that we can use to predict the behavior of this system. The point I want to show or emphasize is that this is a positive action. The effective gauge action that is generated by heavy fermions is positive. As a consequence, the bare gauge coupling beta will have to be decreased to keep the balance, to keep the lattice spacing unchanged. That is, beta decrease will compensate for that. And as a consequence of that, that makes simulations quite difficult because that when beta decreases, UV fluctuations increase. But nevertheless, this is what we call the hopping parameter expansion, and then I was still ambitious and so that people might even do exercises. I suggested to calculate the first term that I already gave here and try to calculate the higher order terms. And let me return, let me not return. What I wanted to do here is actually show that that in the strong gauge coupling expansion, the Wilson loop follows an area law that shows confinement. But I think everybody must be tired enough, so let me not get to that. I will stop here. I am happy to have more discussion or questions.
Any questions? Anyone? Okay, the room is quiet. I think people are still kind of waking up. Thank you so much.
This has been a lot. Hopefully something will stick. I believe
there is a question, yes.
Okay.
Could you repeat the part where you discussed that the IR fixed point should emerge beyond 10? Like why that part was not clear to me.
Okay, like this?
Yes.
But, okay, so we don't know where the IR fixed point emerges. We know that, so what do we know? Sorry. We can look at the two-loop beta function. And two-loop beta function will say that the IR fixed point emerges at NF something like 8.05, so just above 8. But of course, that in perturbatively that emerges at G squared infinity, so nobody trusts that. We don't know where it is. We can look at, for example, we know that infrared-free system shows up at NF 16.5, so that's the largest flavor number that we can have and still have asymptotic freedom. So for example, NF equals 16, nobody doubts is conformal. It has an infrared fixed point that's very small. Perturbation theory is trustworthy. So what we have is somewhere between 16 and 8. Probably there is an infrared fixed point. Okay. Where exactly it is a non-perturbative question, numerical question.
So that analysis has not yet been done. Like you have chosen NF to be 10, right? So is that an estimate you're choosing? So
okay. So let me say that it's a controversial question. There are people who say that NF10 is chirally broken. My results using basically calculating the beta function, not from the data that I am showing here, but from a different simulation, suggests that 10 flavor is conformal. But to be fair, what we can show, we can have a beta function, let me clean that up a little bit, that looks like something like that. So it shows a bending backwards, but we are not able to go all the way to the zero. That's why I could not tell you where the fixed point is, because we just have an estimate based on where the numerical data is. So I believe that 10 flavor or is most likely conformal. That's what the data shows, but I don't have a solid, I cannot show you a beta function. NF12, we actually have a beta function that I trust, and it does look like that it has a fixed point. So I would say that 12 is looks quite solid. 10, one might argue, and if I can advertise, what I am going to talk about on Tuesday is a relatively new investigation with 8 flavors. And you might say that if I don't know what 10 is doing, then why am I looking at 8? There are various reasons, mainly because NF8 is anomaly free, so it can have different phases. And everything at that point that I can see suggests that 8 flavor is actually, or could be, the opening of the conformal window. And if that result holds, and I have to say it needs verification, it's a relatively new result, somebody else has to go there and verify that it is indeed correct. If NF8 is the opening of the conformal window, then of course NF10 will be conformal. But that's where we stand at this point.
Thanks.
Anna, just for interest, I looked up Slava's paper, and they're hard to read and they're complicated. But as far as I can see, he really only deals with the question of the complex pair before you hit the conformal window. There is one cartoon like your last thing, but I don't think he seriously thinks about it. And so, but they're interesting papers. We should actually try to figure out.
No,
I think the fact is he can't do anything there. See, he has this analytic idea of complex conjugate things, and I think there he has a model, and it's mostly an analytic paper. I think he really can't go beyond that. So here's a case for Lattice IISER who's got to come to the rescue.
Yeah. No, I believe you. That's probably correct. The merging fixed points I've seen in Igor Herbut's papers, but that was more a perturbative one.
Who is doing that? Igor who? Sorry.
I think it's Herbut.
I know Julius Kuti was talking about doing it at one point, but I haven't heard anything.
Yeah. So Julius has been talking about it, but I don't think he has actually done anything
beyond I haven't seen anything either.
Looking at it. Igor Herbut did calculations, perturbative calculations in like Yukawa-kind system, 3-dimensional system, where he explicitly could show the merge of the fixed points. But I think that's the closest.
I mean, I actually think, I'm sure you agree that for beyond the standard model, it's really as you approach it that's interesting. So this idea of complex conjugate CFTs looks very interesting. And Slava, of course, in his usual vein, tries to throw cold water on the thing that anybody else is doing. And he says, I don't know if this makes a light scalar, but he also admits that that's a dynamical question which he can't deal with. So again, this is a place for the Lattice to figure it out. So I
think the light scalar is a separate issue, although we always thought that there will be a light scalar if we have working. So
no, in fact, that's what he says. He says there has to be some extra dynamics, and he doesn't discount that it might be there. But anyway, that's what I got from the paper, right?
I agree. We don't know, but I think this phase diagram is what we should be going after. And if the numerical data or results that I have, which rely on finite size scaling and all sorts of other approaches, they really suggest that that this is what we have with 8 flavors. And
Okay.
then we can go and really investigate.
No, that's certainly
Yeah.
very interesting.
But okay,
Any
I think
last
I should
question?
stop
One
now so
last
you
question.
can have these.
Is there any one last question? I think we're done, so let's thank Anna.
Thank you.
And now Richard can finish his conversation.
Okay, right. Thank you. I really miss you guys. It would be fun to discuss more physics, but
Oh, this was great.
even these questions were great. So I try to listen in more, but you know it's midnight for me, so
Sure.
I think I will enjoy your tea. Thank you.
Thank you, Anna. Bye.
Thank you.